Okay. Good afternoon, everybody. Good morning, good evening. I don't know in which part of the world you are. So we are going to start with the course Estudio y Monitoreo de la Ionosfera para el Clima Espacial, which is the study and monitoring of the ionosphere for space weather. And this course is going to be shared. The lectures are Claudio Cesaroni and Lucilla Alfonsi from the INGV, or INGV in English, and they will talk about this very important subject. This course is born during a long-term collaboration with INGV and Universidad Nacional de Tucumán, in this case with the Tucumán Space Weather Center, which is our program in space weather. Here our website and the Instagram page of our group. And in the frame of this collaboration, long-term collaboration, this past week, along with the Servicio Meteorológico Nacional, we have been installing in Argentina two very important equipment for space weather ionosphere. This is what they are going to talk about a little bit more now. And so welcome everybody. And that's for anything you need to know about the course and the certification and anything you need, you can send me an email to that email address. And I think that's it. Thank you very much. And I leave you with Claudio and Lucilla.
Thank you, Graciela. Welcome, everybody. I'm Claudio Cesaroni from INGV. I am a research scientist in ionospheric physics, and I'm at the present the head of the upper atmosphere and radiopropagation group at INGV. So let me introduce Lucilla Alfonsi, who is the other speakers for this very exciting course, let's say. I'm very happy to for this collaboration with Graciela and with the University of Tucumán. That is a long-term, that is a tradition for us. So now we reach the objective to organize these lessons, and I'm very happy of that. So we are going to talk about space weather and ionosphere in particular. We have 3 days, if I am right, 3 days of lessons, a couple of hours each day. So Lucilla is going to start the lessons talking about space weather in general. But first of all, let me say a few words about our institution and our research in Italy. So INGV stands for Istituto Nazionale di Geofisica e Vulcanologia. That is the National Institute of Geophysics and Volcanology in Italy. We are a quite big research institution, public research institution, funded by the Italian government. INGV was founded in 2000, but actually the tradition starts very well in advance with Guglielmo Marconi founding the ING, so the National Institute of Geophysics, and then with the melting of this institution with the volcanic observatory in Naples, INGV was founded 21 years ago. The main goal of the INGV is the assessment and mitigation of the risk related to natural hazard, in particular to seismic and volcanic risk, and the investigation and research activity on all the aspects, let's say, of the geophysical sciences and the understanding of the mechanism controlling the natural hazard and the risk related to this natural hazard. We are basically the biggest European institution related to geophysics, so a quite important institution. the mission of the institute again is mainly related to earthquakes and volcanoes, but we have a quite big number of people that is working on the what we call environmental aspect of the geophysics, and in this framework there is our group that I'm going to talk in a few minutes. For what concerns the personnel, we are about more than 1,000 people, and we are distributed among let's say, scientists, technicians, technological engineering, and administrative people for sure. We are more or less, after a long time of not permanent position for a lot of people, we are now almost all in a permanent position. So we are quite sure that we have the possibility to work with a long-term vision of the research. We have 3 departments: the earthquakes department, volcanoes department, and environment department. The first 2 departments is quite self-explanatory, while the environment, that is the department to which me and Lucilla belong, is involved in a lot of research activity related to very, very different aspects of the environmental sciences. So from the geomagnetism and paleomagnetism, aeronomy, radiopropagation, space weather, polar research, geochemistry, and exploration geophysics. These are not exhaustive list of the research aspect we face in the environmental department. In this department, there is our group, the Upper Atmosphere Physics and Radiopropagation group, including about 20 people among scientists, engineers, and technicians. And we are in charge to manage all the infrastructure and instruments related to the research in the ionosphere and space weather. Our main research topics are basically all the study related to the ionospheric physics, the HF radio communication, GNSS signal propagation through the ionosphere, the coupling of the lithosphere, atmosphere, ionosphere, and all the technical stuff related to the development and managing of the instruments, acquiring the data that are very useful for our research. So this is a very brief introduction to our institution and our activity. So now I leave the floor to Lucilla to start the lessons. Thank you again, everybody, and see you in 1 hour.
Thank you, Claudio. Welcome, everybody, also from my side. As Claudio introduced himself, I would be happy to do the same. I'm Lucilla Alfonsi. I'm a senior researcher at INGV, and my research interests are mainly on the study of ionospheric irregularities for space weather application, but also for basic science, and about the long-term trend of the ionosphere due to the anthropogenic sources, or possibly linked to the global changes. I'm going to start our course with the first block of our course that is related. Our course want to introduce to the space weather concept, and mainly going through the part that impact the ionosphere, or better, how the ionosphere impacts the space weather applications. But to do that, we have to go through the general concept of space weather and space climate, and to go deeper on the sources of space weather and space climate. So at this stage, we decide to go for a leveling course to introduce all the concepts, of course, in a leveling approach, but trying to give you all the ingredients for the receipt. So what is space weather? Can we consider space weather as science or a service? This is the big question. I would say that space weather is both. It depends on the way that we look at the space weather. Here I have write one of the 1,000 definitions that you can find surfing the web. And that reads something like space weather refers to the environmental condition in the Earth magnetosphere, ionosphere, that is involved because it's the protagonist of this course, and thermosphere due to the sun, the solar wind, that can influence the functioning and reliability of spaceborne and ground-based systems and services or endanger property of human health. So there are a number of interests around space weather, and in the recent year, as our modern society is relying more and more on technological services, we have to stress space weather application in such a way to match the need of the users. And also for an economical issue is something that is more and more demanding and more requests from the users. Is a very interdisciplinary discipline in the sense that it involves the space-based telecommunication, the broadcasting, the weather services and navigation, the power distribution and terrestrial communication, especially at high latitude, but not only, the main space mission, the aviation sector, just to mention a few of them. Each of these service domains has the need for space weather data and above all space weather services. So not only data, but some products that can be derived from the data. Together with a further requirement for those services to be tailored to the particular application. We will mention some of these applications if we will have time, also in some details. Several of these services are indeed affected by the ionosphere. This is what we highlight, the ionospheric role. So let's go back for a while to the general definition of weather and climate. So the difference in the two definitions is that for weather and climate, the difference is in the measure of the time. Weather is the condition of the atmosphere over a short period of time, while climate is the atmosphere behaves over a long period or some long periods of time. So weather gives us the information on the way in which the atmosphere is behaving, mainly with respect to the effect on life and human activities. The difference between the two, weather and climate, is the weather consists of short-term, minutes to months changes in the atmosphere, while climate, we are looking at the long-term pattern, so on an average pattern. Some scientists define the climate as the average weather for a particular region and time, usually over 30 years, but this is something that is related to the application, of course. And of course, if you have a climatological description, a climatological picture of your environment, you can use this climatological picture as a background. And with this background as a reference, you can have the taste, you can have the indication, you can detect the weather condition as a difference, as an anomaly, as the difference with respect to the background. So this is why also in space weather, the space climate is a very important discipline, is a very important reference. So what is the engine of space weather? The engine is the sun, of course. And the sun is the driver. And in particular, we care about what is called the circumterrestrial space, the space that embeds our atmosphere, our planet.
So we care about the sun, generally speaking, but above all, we care about how the sun interacts with our space, the circumterrestrial space. So what we have to look at are the solar condition and the solar wind condition towards the Earth. The multidisciplinary aspect of the space weather issues are a good knowledge of the sun, the solar wind, the magnetosphere, the ionosphere, and the thermosphere. So it's a very complicated system made of a lot of chain response. So the sun, our star, these are very general details on the sun, description of the sun, the diameter, the distance from the Earth. As you can see, the temperature is very variable, can be from 6,000 to 50 millions of degrees Celsius. So it's very, very variable according to the different region of the sun. And what we know about the sun are derived from models, because nobody, no spacecraft, no any sensor can reach the sun to our model technology, to our knowledge of today. So what we know about the sun is modeled starting from an empirical assessment that rely on the data that we collect around the sun. From this classification point of view, that see the temperature and the luminosity of the stars, you can see that the sun can be considered a middle star, in the sense that has a middle luminosity and a middle temperature. But for us, of course, it's not the case. It's not a middle cut, is the star. So the structure of the sun, in few words, in a nutshell, the core of the sun. From what we know, every second, the nuclear reactions in the core of the sun transform 700 million tons of hydrogen into helium. The pressure and the temperature are so high that the individual atoms merge with one another, forming helium and producing energy. This is the reaction. And going through the sun, we catalog the different regions as the radiation zone. When the photons travel the speed of light, the density is so high that the photons take 10,000 years to leave the sun from the core. Then there is the convection zone, so-called because it's characterized by the presence of these convection cells going from the inner part of the sun towards the outer part of the sun. Then there is the photosphere that is perceived from our eyes as the sun surface, even if we cannot talk about surface because we are not talking about a solid body, but is a gaseous enormous sphere. So we cannot speak about a real surface, but to our observation on optical wavelengths, the photosphere is the part that we see as the sun surface. And then the chromosphere is the most turbulent regions in which the bulk of the perturbation occurring on the sun that we care about for space weather application generate. So a little bit of history on the observation of the sun. The merit of quite modern, I would say, a modern way to register, to record the activity of the sun was drawn by Galileo Galilei, that starts to observe the sun with bare eyes, only protected by dark lens, and with a telescope, with an ancient, of course, telescope, the ancestor of the modern telescopes. And he drew this kind of paintings on his diaries in which he drawn a circle with a glass. And on that circle, he draws with a lot of details, as you can see from this reconstruction. This is a sequence of drawings by Galileo. This dark spot that he observed on the solar disk. He was persecuted by the church because, according to the age, the sun was considered as a pure, completely white disk without any darkness. So this was considered heretic. And also because looking day by day, at the same day, with the same kind of observation, the evolution of this spot, of this dark spot on the disk, it discovered the rotation. Because if we concentrate, if you veer your attention on a particular spot in this sequence, you can see that that particular spot is moving. And this was considered heretic as well, because the sun was considered standing stuck in the sky. Thanks to this kind of observation, we now know that the solar cycle is a period of time in which the sun starts to have a significant number of spots. These are called sunspots. Then there is a maximum of the occurrence of sunspots, and again there is a decreasing and a minimum. This period of time is called solar cycle, and this lasts about 11 years. What sunspot look like from the space? These are real images from the space, of course, elaborated from computer processing, but these are real images. These are dark spots on the solar disk because they are colder area with respect to the surrounding areas, because there is an anomaly of the solar magnetic field that make this zone colder with respect to the environment. So why this is why they appear on optical wavelength as dark regions. Here you can see the reconstruction from the observation. The yellow, the blue, and the red solid line give you the daily, monthly, and monthly smoothed sunspot numbers as observed and as derived by the simple formula that you have at the bottom left, in which you see appear the number of the groups in which the spots appear, and the number of spots for each group, and K is the variable that account for the system, the observing system and the observing condition. This cycle can be also predicted nowadays. And in fact, you can see in the same plot also a prediction of the sunspot number, so a prediction on how the cycle would go. We are now living the so-called ascending phase of the solar cycle. So we are seeing an increasing number of sunspots, an increasing number of perturbations coming from the sun. The two dashed lines identify two different models for predicting the solar cycle. Of course, the new era of the knowledge about the sun was opened by the observation from the space of the sun. And so was the grandfather or the grandmother, as you usually prefer, of the solar mission. The orbit of SO that you are seeing the movie on the right is such to see always the interaction between the sun and the earth. And this is possible because SOH is flying around the L1 Lagrangian point that you see in the picture on the left. This is a point in which the spacecraft is in equilibrium and oscillates around that orbit that you see in the movie, and is capable to be always in line between the Sun and the Earth. So in this case, SOH can observe always what is happening around the Sun, but in the direction towards the Earth. And these are examples of images provided by the SOH mission that I forgot to say that is a European Space Agency and NASA Space Agency collaboration mission. SOH provide this kind of different images of the Sun that are taken at different wavelength from different sensors on board the spacecraft. And as you can see, they have different colors. Of course, the colors are not real, but they give these colors because there's a code, as you can see, of the different wavelength and the different temperatures that over which the information are taken. So they can really reveal complementary phenomena. And the solar cycle from the space, you see, from these two movies from SOH as well. On the left, you see a movie of the Sun taken on December 1986. And on the top, you see from the arrows that we are in the decreasing phase, approaching the minimum of sunspot number, while the other movie relates to June 1999, in which we were almost at the maximum of the solar cycle, the other arrow in the top plot. And you can perceive the big difference between the two movies, in which you have a low solar activity on the left and a high solar activity on the right. So the difference is very evident. So about some perturbation, we will mention just a few, the most important. These are flares. Flares are intense explosions happening on the Sun that release energy in the outer space. The typical wavelength is the X-rays, gamma rays, and radio waves. Then we mentioned the coronal mass ejection, the spectacular coronal mass ejection that you can here see in two pictures, in two movies from SOH as well, from the SOH spacecraft. The one on the right, you see that was so violent, so rich of energetic particles that saturate the sensor on board the spacecraft, giving this noise on the image. The shadow on the left of the movie, you see the boom of the spacecraft, and at the center of the movie, you see this disk that is used to hide the solar disk, to concentrate the observation in the surrounding area, to isolate the corona of the sun, and to see the emission. These are a very violent emission, and very often flares are accompanied and associated to solar mass ejection. And the last one that I would like to mention among the solar perturbations are the coronal lords. This region, again, in the corona of the Sun, appears dark because, again, they are associated with the open magnetic field lines of the Sun, so are darker because they are colder with respect to the surrounding area. And from this area, this zone, you see in this case a big hole in the polar, in the North Pole of the Sun. From this region of the Sun, are released streams of high-speed solar wind, and we will see in few slides what is solar winds in detail. So why this emission don't go along straight lines instead of having this lobe configuration? This is because the energetic particles leaving the sun are compelled, are driven in their path leaving the sun in the outer space according to the field line of the sun, that, as you can see, is originated at the sun, but with a differential, but due to the differential rotation of the sun, that is due to the fact that it is a gaseous sphere, don't have the same periods of rotation, but you see from the left picture, you have a rotation of 25 days at the equator of the sun that rise to 35 days at the poles. So this kind of differential rotation gives these big anomalies in the actual configuration of the solar magnetic field. And the particles leaving the sun follow these field lines, and this is why they have this lobe-like geometry. In this model of the sun, you can see the big picture of the solar magnetic field and how the perturbation look like according to the magnetic field configuration. So, questions? Take a while for having some water. Claudio, any question for us? Not yet. Yes, you can. Graciela is suggesting that you can open the mic and you can write on the chat whatever you want. Please go ahead. Don't be shy. There are only silly answers, no silly questions. Okay, so I can go ahead. Okay, so we have mentioned the words solar wind. So we are entering this in this part of the solar description of the solar Earth interaction description. So traveling from the sun to the Earth, we cannot mention, of course, the existence of the solar wind. What solar wind is? The solar wind was named as wind in comparison in comparison with the neutral winds to describe this flux of solar particles coming from the sun in the outer space, but in this case we are seeing the solar wind investing the circumterrestrial space. These are particles, energetic particles that moves at supersonic speed, and that when they encounter, that they approach the circumterrestrial space, they cannot go directly towards the Earth, but the solar wind is deviating the path, as you can see from this animation, and we will see why. The solar wind follows the lines of the magnetic field generated by the sun that we have already seen in the previous slides, and the geometry of this propagation from a geometrical point of view is called the Archimedes spiral, and is called also the ballerina skirt, because it's very similar to the movement of a ballerina skirt. And in this, model of the solar wind. You see at the center of this movie, the sun that is emitting the solar wind continuously. You see this green, light blue flow from the sun, that is the quiet solar wind. And at certain time, it happens a coronal mass ejection, leaving the sun and moving in the outer space. And there is, as a yellow small dot, you see the Earth. And so the ballerina skirt can be also embedded into an additional booster that is provided by the occurrence of this coronal mass ejection phenomena. To study the interaction between the solar magnetic field and our magnetic field, so the geomagnetic field, we need to use a reference system, a geometrical reference. And what I would like to say is that the solar magnetic field is called interplanetary magnetic field, because the interplanetary magnetic field is essentially due to the solar magnetic field. So the two fields can be considered as one field. So the interplanetary magnetic field can be described as a vector in which we can describe its components according to a Cartesian reference, in which a plane, the Bx and By plane, is the plane of the ecliptic, and the Bz axis is the vertical with respect to this plane. And Bz is taken as positive northward and as negative southward, and is particular to the date. So the solar wind main feature are listed in this table. These are typical parameters of the slow solar wind, so of a quiet solar wind. The speed is 350 kilometers per second. And there are also the density, the composition, as you see, the majority are protons, the proton temperature, the electron temperature, and the magnetic field. This is the solar magnetic field that we call the interplanetary magnetic field. The existence of the solar wind was given by Eugene Parker in 1958. That saw his discovery rejected in several journals, several scientific journals, and at the end, a proofreader saved one of these attempts that he made to publish his results, and finally he succeeded to publish his discovery. The solar wind plasma dynamic pressure is much higher than the magnetic pressure and the thermal pressure. So we can consider the interplanetary magnetic field as frozen in the solar wind. So measuring the solar wind means also measuring the interplanetary magnetic field. And the two stickers on the right represent the two missions that provided the data of the solar wind. The former mission was ACE, the Advanced Composition Explorer, that was replaced by the Discover mission. In the plot, you see at the top the three components of the interplanetary magnetic field along 6 hours of a certain time during the storm, the geomagnetic storm occurred in 2015, March. And then there is, in the middle plot, there is the velocity of the solar wind, and at the bottom there is the density of the solar wind. If you draw your attention on the middle plot, you see the jump of the velocity of the solar wind from around 400 kilometers per second, reaching 500, with peak reaching also 600, 550 and more. These jumps are typical of the condition that we have seen in the previous slides with the ballerina skirt. When the solar wind from slow accelerate to fast, this happens because there are some booster from the sun, as happened during the release of coronal mass ejection. This is typical. This big jump, as you see, the jump is instantaneous, is in a while, is immediately evident on the sensor of the spacecraft. So, questions, comments?
What is the jump? Yeah, one.
You see the jump on the velocity? BZ, yes, we will see. We will see in the next slides, and Claudio will talk about this. The BZ component is the most important for space weather studies and also for the space weather application.
There's a question in the chat.
Yes.
Why the wing of the propagation of the solar wind occur in the direction of Earth and Mars and not in the other direction?
That was by chance. We don't know why. There are sometimes perturbations that are occurring towards the Earth or other planets. But what we care about the terrestrial space weather is to look at the perturbation occurring towards the Earth. This is why I have selected that particular representation.
This is what we call the geoeffective CME. So in the case of the emission of the particles in the direction of the Earth, so if the accelerated solar wind can reach the Earth, we talk about the geoeffective coronal.
Because it's affect the Earth, so it's effective on the Earth. That is a matter of definition. Other questions?
Just a comment, the explanation was perfect.
Ah, wow, I'm very happy. So now I give the word to Claudio. Maybe. I give the word to Claudio. So as you have seen, we are traveling from the sun towards the Earth. So we are approaching the circumterrestrial space.
Yeah, so we are moving from the sun and the phenomena occurring on the sun, on the corona, especially due to the disturbances in the magnetic field of the sun, moving through the Earth, moving up to the Earth through the interplanetary space. So we saw with Lucilla that the main, the main messenger for the disturbances occurring on the sun is the solar wind propagating from the corona down to the magnetosphere. So let's see what the magnetosphere is. We all know that the Earth has its own magnetic field that can be represented as a first approximation as a dipole magnetic field. So like the magnetic field generated by a magnetic bar that is not along the north to south geographical direction, but it's slightly tilted with respect to the geographic north and south direction of about 11 degrees. So what you see on the top right image is the approximation of a dipole magnetic field. And the magnetic bar superimposed on the Earth is the ideal source of the magnetic field of the Earth. These magnetic fields describe a region in which the magnetic field affect the particles and wave moving in this region, and this region is called magnetosphere. So the region in which the Earth magnetosphere bounded by the pressure of the solar wind, is able to impact the movement of the particles and the propagation of the electromagnetic wave is called magnetosphere. If the, the source of the magnetic field was a perfect and ideal magnetic bar, the magnetosphere looks like the image you can see on the bottom. But the real magnetic field is not like this, and we will see in few minutes the real shape of the magnetic field. So how to define, how to measure, how to give a quantity description of the magnetic field. In this sketch, you can see the different way the scientists used to define the components of the magnetic field, that is represented here by the arrow named with F. So F is the total magnetic field, and F is the intensity of the total magnetic field. As you can see here, this arrow is embedded in a reference frame that is given by the geographic direction, north, east, and the vertical downward direction. That is here represented as X, Y, and Z respectively. So X, Y, and Z component is the direction of the geographic north, east, and downward, pointing to the center of the Earth. So if we project the F, so the total magnetic field, on the horizontal plane defined by the X and Y component, we can obtain what we call the horizontal component, as here indicated as H component. And the angle between the total magnetic field F and the H component is called magnetic inclination, here represented as phi. So the magnetic inclination is a very important parameter to define the orientation of the magnetic field, and we will see tomorrow the day after tomorrow, and during the third lesson in particular, how important is this angle to define all the dynamics ruling the ionospheric plasma. So by projecting the H component, so the horizontal component, along the north direction, so along the X direction, we can define another angle that is the magnetic declination. That is basically the difference between the geographic north direction and the magnetic north direction. And I don't know if you are familiar with nautical maps, but in the nautical maps there are always the line representing the same declination. Why? Because with the compass we are able to follow the magnetic north, but we want to know how the geographic north is. So knowing the declination, we can obtain the geographic north direction by measuring with the compass the magnetic north direction. In equation, basically, if you compose the X, Y, and Z component, you can obtain the total intensity of the magnetic field. And if you compose only X and Y component, you can obtain the H component of the magnetic field, that is the component of the field on the horizontal plane. Is it clear, the definition of the angles and the components of the magnetic field? This is a very crucial point because we are going to use this angle and components very often. So please interrupt me if something is not clear. We said that the magnetic field can be imagined as a dipole magnetic field, but it's not true. I mean, the magnetic field is generated, as you already know, by the convective current inside the Earth. So this current is generating a quasi-dipole magnetic field that is perturbed by several factors. That is the magnetic field generated by the Earth crust, that is the phenomena coming from the outer space. So even the space weather events influence the shape of the magnetic field. So what we did in the past and what we do is to define a model of the magnetic field that is coming from the measurements of the magnetic field taken on the ground by some instruments called magnetometers, that are basically coils that are able to measure the currents generated on the coils by the magnetic field. So this suggests to us that a measure of the magnetic field is actually always a measure of occurrence, and vice versa. If we want to infer a current in the ionosphere, for example, as we will see in the next days, we can measure a magnetic field. So magnetic field and currents are strictly related, as the law of the Biot-Savart suggests us. So to define this model, we usually use what is called a spherical harmonic decomposition or model of the magnetic field. So you can imagine that we have some measurements in some specific points of the Earth, but we want to define and to describe the magnetic field all over the world. So we can in some way interpolate or model these measurements in order to obtain a quite homogeneous description of the magnetic field. And we did it by using this spherical harmonics description. Here you can see the equation defining the spherical harmonics. I don't want to go into details of this, but just to mention that is this V, that is the potential related to the magnetic field, is described by as a function of the R, that is the radius, the latitude, longitude, and time. So from this we can infer that the magnetic field is not static, is not homogeneous, is not isotrope. I mean, we have variation related to space, so latitude and longitude, but also variation related to time. And this variation related to time is going on in very, very different time scales. So we have variation of on a time scale of seconds that are mainly those one related to the external forcing, so to the space weather events, as we will see. And we have variation, what we call secular variation, that is given by the very slow variation in the convective path in the interior of the Earth. So here you can see on the left the total intensity of the magnetic field described by this model. That is not a dipole magnetic field, as you can see. And on the right, you have the H component of the magnetic field. So the horizontal component of the total magnetic field. Why we are showing the horizontal component? Because as we can see, the horizontal component is the one that gives us the possibility to define the disturbances induced by the solar wind on the magnetic field. I mean, the solar wind mainly impact on the H component of the magnetic field. Just for sake of curiosity, we are not going to talk about this stuff, but as you can see on the left figure, you have this huge blue spot. That is a region in which the magnetic field is very low with respect to the surrounding region. And this is what we call the South Atlantic magnetic anomaly. That is an anomaly of the magnetic field that is not very well understood so far. But this anomaly, this very low magnetic field, is moving with a very slow velocity, and is now on the region of the South Atlantic Ocean. So this is why we named like this. And this is, I mean, if you look at the plot of the magnetic field, you can see that the, I mean, this region has a magnetic field that is very low with respect to the surrounding one. So we can see the, I mean, we will see the way in which the particles are able to reach the Earth by the solar wind to the Earth. But consider that this region is one of the region in which the particle can enter into the magnetic field and reach the ionosphere. Not like the poles, but it's a region that is very affected by the particles coming directly from the sun. So, as already mentioned, the magnetosphere is the region in which the magnetic field of the Earth, confined by the, bounded by the solar wind that is coming from the sun, dominates the motion of the charged particles and the propagation of the electric field. In this video, you can see how the magnetosphere, why the magnetosphere has this shape. Because if you consider a dipole magnetic field, the lobe of the magnetic field line should be symmetrical in some way. But the presence of the solar wind is giving this particular shape to the magnetosphere. So we have a very compressed magnetosphere on the on what we call magnetic noon. So that the direction in which the magnetic field faces the sun, and so the solar wind is impacting on the magnetosphere by compressing the magnetosphere and by stretching the magnetosphere on the other side. And this is what we call magnetotail, because it's like a tail of a comet. So we have the, in principle, the dipole magnetic field and the solar wind that is shaping this magnetic field, giving this particular shape to the magnetic field. So compressing the magnetic noon and stretching the magnetic midland. And okay, so as Lucilla said, the solar wind is basically a flow of particles, of charged particles, that is coming from the sun, propagating through the interplanetary magnetic field and impacting on the magnetosphere. So in principle, this magnetosphere is a kind of shield that don't allow the particles to reach the Earth. So the solar wind can flow at the boundary of the magnetic field. But due to the particular shape of the magnetosphere and the interaction by the solar wind and the magnetosphere, it could happen that some particles can reach the Earth. So here in this sketch, you have the two different situations when the solar wind, let's say the solar wind of a CME reached the Earth, reached the nose of the magnetosphere. So you can have the BZ component of the interplanetary magnetic field north or negative, so pointing south. And this makes a huge difference in the magnetospheric configuration. Because if the BZ is positive, so the interplanetary magnetic field component is northward, we have what we call closed magnetosphere. So basically, the solar wind magnetic field and the magnetic field of the Earth is not connecting each other. So the particle cannot enter in the magnetosphere, cannot reach the magnetosphere and the ionosphere and the Earth. In the case of, and this is the sketch on the top of the figure. In the case of southward interplanetary magnetic field, so the BZ is negative, the solar wind and the magnetic field of the Earth is connecting each other. So basically what happened is that the field line of the interplanetary magnetic field is connected with some of the field line of the magnetic field. So this way, in this sense, the magnetosphere is open. This doesn't mean that the magnetic field line are open, because we know that the the line of a magnetic field is always closed. But in some way, the magnetosphere is open in the sense that it allows the particles coming from the solar wind reaching the magnetosphere and then the ionosphere. And this is crucial for our study, because we will see that in case the particles reach the ionosphere, this particle can influence a lot, can impacting heavily the ionosphere, the morphology and dynamics of the ionosphere, especially at the polar region. Why? Because if you imagine the shape of the magnetic field and the way in which a charged particle is moving along a magnetic field line, so a kind of spiral along the magnetic field line, you can see that when the magnetic field of the sun, from the sun, and the magnetic field of the earth connect each other, the particles can flow along the magnetic direction. And the magnetic field are the footprint of the magnetic field, in this case, is on, always, but in this case in particular, is on the polar region of the Earth. So the particles is moving along the magnetic field line and is reaching the Earth at polar region. So if you have clear this kind of connection of the magnetic fields and the movement of charged particles along a magnetic fields, we can define now different, let's say, region in the polar ionosphere, in the high latitude regions. And this is very useful for our studies, because this region define different dynamics and different phenomena ruling the ionospheric movement there. So when the region in which the particle reach directly from the solar wind to the Earth, reach directly the ionosphere, we talk about polar cusp. That is the point. Okay, if you look at the left plot, you can see the black region. That is the polar cusp. So basically, it's a region close to the magnetic North Pole, but facing the sun, so at the magnetic noon. This is a way we used to define a frame of reference by using the magnetic local time. Just to spend a few words on this, if you look at the left plot, you can see here we have 12, 6, midnight, and 18. This is the magnetic local time. So basically, the noon is the direction in which the magnetosphere is facing the sun, like the noon, the noon we already know. And then we have the midnight sector, and then the dawn and dusk. So with this magnetic local time, we can define some regions that are interesting from a magnetic and ionospheric as well point of view. Then when we have a region in which that is the boundary among the let's say normal field line and the ones stretched by the connection of the magnetic field of the Earth and the magnetic field of the sun, that define a region that is called auroral oval. That is the gray region in the left plot, and this is the region in which this is why the name, the aurora, is more likely to occur. And what is inside the inner boundary of the auroral oval is named polar cap. So the polar cap is the region inside the inner boundary of the auroral oval. Okay, so we have seen that all is clear so far. So maybe some questions. Yeah. Yeah.
We know the evolution of the plasma parameters of the distances was nominal units because I have shown just in one.
At L1. Okay. Basically, what we know about the interplanetary magnetic field and solar wind is the measurements we have at L1. So this is why it's so difficult to have a forecasting of the solar wind parameter and the interplanetary magnetic field parameter, because we can measure the solar wind when the solar wind is very close to the Earth. If you remember the image of the gravitational potential, and so the L1 point is yeah.
I go back, I quickly answer on the fact that we can model a propagation at different distances, but what we have in our hands are all the observation at this dimension.
Yeah, so there are several models that are trying to model the solar wind velocity mainly, and the interplanetary magnetic field, starting from the optical observation of a CME. So, but there are very let's say rough model. I mean, what we can do so far is to try to infer the velocity of the plasma coming out from a CME and propagating this velocity more or less with a very basic physical law through the till the magnetosphere, and that's it.
As the model on the side of the ballerina scroll, there was a model of propagation, but this propagation model is based on the poor actual data that we have.
Yeah.
There are other questions.
Mm-hmm.
What the solar wind affect mainly the H components and electrons?
Okay. So as you can see, okay, the answer to the first question is very complicated, but basically the H component is the one. First of all, the near the equator and at mid latitude, basically the H component is the mainly component of the magnetic field of the Earth. So, and then what is driving the interaction by the solar wind and the magnetic field is the Z component of the magnetic field. So in some way, if you remember the very basic law of the magnetism, this is impacting to an orthogonal component of this field. So basically, I mean, this is not true. I mean, it's not only the horizontal component that is affected by the solar wind and the interplanetary magnetic field, but this is the one mainly affected and the one we use to define the disturbances induced by the solar wind. So as we are going to see in a few minutes, when we define the geomagnetic indices, that are something that is useful to define to quantify the disturbances induced by space weather events on the magnetic field, we are using always H component. And the other question is at any latitude. No, I mean, in the polar region, namely the H component of the magnetic field is 0. So this is not useful to define the disturbances on the magnetic field on the H component at the polar region. And this is why we use another index at the polar region. But I mean, On the other latitude, especially at low latitude, yeah, the H component is mainly affected by the solar wind.
Okay, then there is the one thank you for the explanation. So there is a Mira, that is asking.
Ciao Maria.
Is asking if you can read the definition of the overall.
Okay, so let me go. Okay, if you have a look here to the right plot, you can see this region in which maybe you can you see the pointer there? Can you check if okay, so here in this region there are a region that are named in which the particles with a specific energy are trapped. So this particle is moving, is moving along the magnetic field here, the magnetic field line here, and the footprint of this magnetic field line is defining the boundary of the auroral oval. So if you go inside this region, you see the magnetic field line can be represented as a quiet magnetic field line. So, I mean, the magnetic line as the disturbances was not there. And outside this region, you have the particles that are directly entering into the ionosphere. So the boundary of these two regions is defined as the auroral oval.
There is another question.
Very happy?
Marco Guarda, is someone according
To the magnetic?
axis movement.
No, basically not. There are some studies and very cool animation that is showing you the movement and the reshaping of the South Atlantic magnetic anomaly. The movement is, I mean, this is not clear. The origin of this anomaly is for sure related to the inner part of the source of the magnetic field. So there is some disturbances in the convective part of the inside the Earth, but it's not clear. So it's not clear the origin and it's not clear the movement. So the answer is basically not.
Okay.
Good. So we have seen that the interaction between the interplanetary magnetic field and the Earth magnetic field is crucial to define. Yeah. Sì, mi è stufato, Matti. We will see it, yeah, for sure. We will see maybe few slides or the day after tomorrow, but for sure in the third lesson we will see the effect of a magnetic storm, of a solar and geomagnetic storm to the ionosphere. So the answer so far is yes, but we will see in detail. I mean, when the solar wind and the magnetic field of the Earth is continuously interacting, but when something happened on the sun, as Lucilla mentioned, the CME or a flare or some disturbances on the magnetic field of the sun, inducing an acceleration and more dense solar wind propagating from the sun, we have what we call a geomagnetic storm. So basically, the solar wind, when the BZ is southward, so do you remember? the interplanetary magnetic field Z component can be northward, and we have the closed magnetosphere, or southward, open magnetosphere. So in this case, as we have seen, the particles from the solar wind, and so the energy from the solar wind, is injected into the ionosphere directly, because the magnetosphere is open to the solar wind. So when the solar wind is entering to the magnetosphere, and the particles and energy is injected in the magnetic field and into the ionosphere, we have what we call the geomagnetic storm. So a geomagnetic storm is a change in the solar wind that produce major changes in the current system, in the plasma, and in the Earth magnetic field. So this geomagnetic storm is something very important. So our lessons are mainly dedicated to the effect of a solar and geomagnetic storm into the ionosphere, because it induced very, very, very huge changes in the morphology and in the dynamics of the ionosphere at all latitude. I mean, the energy is directly injected at high latitude, but the effects of a geomagnetic storm is visible and can be huge at whole latitude for different reasons, as we can see. So, okay, I anticipated this slide. So basically, again, we have the effect of the solar wind when BZ is negative in the video. As you can see, the magnetic field lines are broken by the solar wind, and some magnetic field line connecting to the solar wind, and then to the magnetic field again on the tail of the magnetosphere here again, and now in the video. And here is what we call the magneto-tail reconnection. So this effect is the effect of this reconnection is to accelerate the particles from the magneto-tail directly into the ionosphere. And this is the main driver of the aurora. So the particles coming, very energetic particles, very fast particles coming from the reconnection on the magnetotail are able to reach the ionosphere in the aurora oval, and you can see the beautiful aurora. But we will see on in the next slide, maybe. So now we said that the a geomagnetic storm is able to change the magnetic field, but also the currents flowing into the magnetosphere ionosphere system. And this is a sketch of the main current that are present in the magnetosphere and the ionosphere system. As you can see, and this is a simplified one, but you can see that is again a very complicated scheme. So I want to draw your attention in particular to a couple of this current. That is the field aligned current, FAC, that are the current that are following the magnetic field line, so field aligned, into the ionosphere at the polar region, and the ring current, that is the current that is flowing at equatorial latitude. This ring current is basically related to the fact that in the solar wind you have ion and electrons, so particle with opposite charge. So when this particle reaches the magnetic field separates the ion and electrons, and the ion and electrons flow in the opposite direction, and this is creating current. Okay, so this is mainly the source of the ring current. Why the field aligned current and the ring current? Because these two current system is the one that is perturbed by the solar wind in case of a geomagnetic storm, and this is used on this is or better, these are the sources of the disturbances we are going to measure with the indices I'm going to introduce you. Okay, so please remember, field line current flowing along the magnetic field into the polar ionosphere, and ring current flowing at equatorial latitude. Okay, so here we have an example of the components of the magnetic field registered by our observatory in Lampedusa, that is a small island southern of Italy, in which we have a magnetometer there. It's a mid-low latitude station. So here you can see the variation on the components, in particular on the H, D, Z component and total intensity of the magnetic field. And this is, I mean, a variation induced by, let me see, I'm not sure. No, okay, this is a normal variation of the components of the magnetic field. So just to show you that we are able to measure, I mean, the single components of the magnetic field by using a magnetometer. Okay, we can maybe go ahead. I stopped several times. So let's move to the indices. So we have let's imagine we have a CME that is leaving the sun. So the solar wind is accelerated, is more dense with respect to the quiet condition. So we have a higher velocity, higher density, higher temperature, the solar wind. So, and the solar wind is coming up to the Earth, and is reaching the magnetic field. So how to measure the disturbances, how to quantify the disturbances induced by this solar wind into the magnetic field? We use what we call geomagnetic indices. That is a simple way to characterize the intensity and the, impact of a geomagnetic storm on the Earth magnetic field. So the first one is the KP, so the K index at a planetary level. So the P stands for planetary. That is a very old magnetic indices that is basically related to the variation of the H component of some subauroral magnetometer. So imagine that you have a chain of magnetometer. There are a lot all over the world. If you take some magnetometer in some specific location at a subauroral latitude, so let's say mid-latitude in some way, you can define these KP indices by looking at the variation induced by the storm to the H component of the magnetic field with respect to the quiet condition. So what we did basically is to consider some quiet days, and basically we use the 5 quietest days for each month. We use these quiet days, the measurements from this magnetometer in these quiet days as a baseline. So basically we are able to subtract to the measure what we call the regular variation of the geomagnetic field. As you can imagine, the geomagnetic field has some regular variation that are from the daily variation to the secular variation, but these are not related to the storm. So we want to quantify the impact of the storm on the magnetic field. So we have to subtract to the measurements the quiet condition magnetic field. So by subtracting this baseline, we are able to represent the deviation of the magnetic field, the horizontal component of the magnetic field. And if we bin this variation in several range, we can obtain what we call KP indices, KP index that comes from 0 to 9. So basically, when we have a KP lower or equal to 3, we have quiet condition. Basically, from 4 to 6, we have what we call moderate geomagnetic storm, and higher than 6, so 7, 8, 9, we have what we call a strong geomagnetic storm. So this is a simple way to define the variation of the magnetic field induced by a magnetic storm. And this is useful in particular at mid-latitude, because we are using measurements at mid-latitude. Okay, and the dynamics of we can, in principle, divide the magnetic field and the ionosphere as a consequence in 3 main regions. So the equatorial and low latitude, the polar high latitude, and mid-latitude. So for mid-latitude, we use this KP index. The next one is the index we use to quantify the effect of a geomagnetic storm at low latitude. And this is related to the variation of the ring current. This is why I draw your attention to the ring current before. Because this ring current, when the solar wind hit the magnetosphere and the BZ is negative, this induces a current that is that flow in the opposite direction with respect to the ring current. So the net effect is that the ring current is decreased by the solar wind impact. And in fact, the variation of the variation of the ring current in this case is taken into account by defining the DST index. That is an index that comes from the measurements from different magnetometer at low latitude, so close to the equator, the magnetic equator. And again, here we have a baseline, that is the wide condition magnetic field variation that we subtract to the measurements, and we obtain the variation, the deviation with respect to the quiet condition that we can define as an index, as a DST index. This time, this is not a real index. Let's say this is a measurement. The KP is a dimensionless index. The DST is measured in nanotesla. So this is a real variation of the magnetic field. So basically, just to be clear, we have the solar wind negative BZ. Solar wind hits the magnetosphere by inducing a current that is opposite to the ring current. The net effect is a decrease of the ring current and a decrease of the magnetic field at low latitude. This is why the effect on DST of a geomagnetic storm is a decrease of the DST, as we will see in the next days. So for low latitude, we have DST index. For mid latitude, we use KP index. The last one is an index we use to define the effect of the geomagnetic storm at auroral latitude, and is related to the field aligned currents. If you remember the sketch of the current system, the field aligned currents are the ones flowing along the magnetic field into the ionosphere and out from the ionosphere. So here you have a sketch of the field aligned currents and how these currents induce currents in the ionosphere. So basically, if the conductivity of the ionosphere was perfect, homogeneous, you will have only Pedersen currents. So basically, the field aligned currents are flowing in and then out from the ionosphere. But the inhomogeneous conductivity of the ionosphere induce also orthogonal currents that are the Hall currents. So these two different currents at 9 degrees each other induce a movement of the ionospheric plasma at auroral latitude that is called that are called convection cell, because if you can see the shape of the movement is we call a convection pattern, and this is what create what we call the auroral electrojet. So the field line current and the inhomogeneous ionosphere create a system of current in the ionosphere flowing at auroral latitude. And this is called auroral electrojet. So to define the disturbances induced by a geomagnetic storm into the high latitude ionosphere, and in particular into the auroral electrojet, we use the AE index. That is, again, basically, just to be general, the variation of the magnetic field induced by the storm measured by magnetometer at aurora latitude. In this case, only on the northern hemisphere, because in the southern hemisphere we have the Antarctica, so the measure of the magnetic field there is very recent. So historically, the auroral indices is given by exploiting measurements on the northern hemisphere. Okay, so summarizing, we have KP, mid latitude, DST, low latitude, AE at high latitude. So how a geomagnetic storm looks like by looking at these indices. Here you have an example of a magnetic storm that occurred on May 2003, and here you have on the top right plot the behavior of the KP. So as you can see, it's from 0 to 9, and at a certain time the KP became higher. So the three colors here, green, yellow, and red, are giving you an idea on how the KP is disturbed. So how the magnetic field at mid latitude is disturbed. So when we have a KP greater than 4, we can say that we have a geomagnetic storm ongoing. On the DST, instead, you have a different behavior that is quite complicated. I mean, as you can see here, we have a geomagnetic storm occurring in 16 of July 2017. And as you can see, the first reaction of the DST to the arrival of the solar wind is an increasing in the DST. But I said before that the DST is coming down when a geomagnetic storm occurs. So this is why the first effect of the solar wind, of a dense, high speed solar wind impacting the magnetosphere, is a compression of the magnetosphere. So if you have a compression of the magnetosphere, as a result, you have an increasing of the magnetic field at ground. And this is what we call, this is what we call the sudden storm commencement. So this peak on the DST is the sudden storm commencement. Then the DST, as we expect, decrease. So this phase in which the DST is decreasing is called the main phase of the storm. And then we have the DST that slowly recover to normal condition, and this is what we call the recovery phase of the geomagnetic storm. And on the left plot, you have the effect of a storm on the auroral indices, not only AE, but you can see here AU and AL. There are other indices, but it's quite close related to AE. I mean, it's just a way to measure the auroral electrojet in one direction or in another. And when we have the auroral electrojet that is greater than, let's say, 400 nanotesla, we can say that we have a geomagnetic storm ongoing. So as you can see here from these three indices, we are able to know if a geomagnetic storm is occurring. So if something is happening by the interaction of the solar wind and the geomagnetic field. But we will see this stuff in details during the third days of the lessons. So here, just an example of the solar wind, interplanetary magnetic field, and geomagnetic indices during the storm. That is the St. Patrick's Day storm in 2015, and we are going to see in details, to study in details this storm. But as you can see, the dashed line is the moment in which the solar wind, the disturbed solar wind, reach the magnetosphere, and in fact you can see a perturbation on the an increasing of the interplanetary magnetic field, an increase of the density of the magnetic field and the temperature. And as a consequence, you can see after a while, let me see if, no, okay. We have an increasing in the CMH index. So the CMH index, sorry, we have the CMH here, but it's the same of the DST, more or less. Okay, so you can consider this plot, the one before the last one, as the DST. So we have an increasing of the DST, so the sudden storm commencement, and then the main phase of the storm. At the same time, you can see that the auroral indices that are on the last plot is, going to be disturbed, so different from zero. Here, okay, this is the arrival of the first CME, but we will see it in detail, so don't worry about it. And here we have the arrival of the second CME. So if you look at the DST, you can see that you have the first main phase here. Can you see the pointer? So there's the first sudden storm commencement, then the main phase, and then another. Here it seems to recover, but then we have another CME that is coming, so the DST goes down again, and then slowly recover to normal condition. So this is a very, this was a huge storm. So the main storm of the solar cycle 24, that is widely studied. I mean, there are hundreds of scientific papers studying this storm, but this is the storm we are going to study the third day of the lesson. So we will see in details.
So we have a question from Sylvain.
Mm-hmm.
Why is AP used as a concept of the solar, for example?
No. I mean, I made myself not clear. All the indices I have shown is used to define the disturbances induced by solar and geomagnetic storm to the magnetic field of the Earth. So, if you want to, let's say, analyze the effect of a disturbed solar wind to the low latitude ionosphere, it's better to use the DST. If we want a general idea, so at mid latitude all over the world, it's better to use KP. That is the more rough index among the indices. If we want to analyze the, for example, energy directly injected into the ionosphere by the solar wind, it's better to look at the auroral electrojet, the disturbances on the auroral electrojet, and so to the AE index and the related indices.
Yes, I would like to add with the explanation given by Claudio that these are tools for us to study the event, the indices, but are just conventional tools, in the sense that they are derived from actual measurements, but they are just tools to understand if storm is happening, and how intense is the storm, and what are the general characteristics of the storm. From that point, we can go ahead in a deeper detailed study of the storm, looking deeply at the data, at the measurements and the observation. And again, when we want to model, predict, for instance, an event, we can make use of the indices. But indices are just a tool, something that can help us. For instance, if you remember from the picture shown by Claudio of the KP index for the storm of 2003, you see that NASA used this color code color code representation of the index, just to give us a first glance the impression of some condition on the boundary or quite condition given by the geomagnetic field that middle latitude. A little bit different from the other two indices that, as Claudio said, they are directly derived from the observation, from the variation of the H component of the geomagnetic field. But anyhow, these are only indicators. So this is the starting point to study event and can be of great help to predict, to model, and to possibly also to mitigate the space weather effect. Other
there is another question related to the temperature reported here. This temperature is the solar wind temperature. So here we have all these parameters are related. Okay, so the first parameter, the one indicated with B, is related to the interplanetary magnetic field. So the total intensity, first, the X, Y, and Z component. Then we have the density of the solar wind, the temperature of the solar wind, the velocity of the solar wind, the DST or CMH index, and the auroral indices. So this temperature is the temperature of the solar wind. This is something that is related, as you think about the definition of temperature, to the kinetic energy of the particles in the solar wind.
So we can ask CMH and DST are the same.
Okay, are not the same. I mean, DST is okay. The CMH is defined by looking at the CMH stands for the symmetrical H. So is done by looking at the day side of the at the measurements on the day side of the Earth. But it's more frequent than the DST. So the DST is given at 1 hour time resolution. The CMH is available at 1 minute resolution. So this is why here we have the CMH. But to study a geomagnetic storm, I mean, at a first glance, it can be considered as completely the same.
Closer to the mic.
I would like also to comment that, of course, for space weather application, the real time or the quasi or the near real time is very important. So to have this kind of indicators, the geomagnetic indices in this case, in real time is a very important source of information for us, because the users of the technologies that are affected by space weather events, they want to know in real time or near real time the information to alert them, for instance, about some kind of disturbances that are coming to affect their technologies. So the indices help also in this direction.
Okay. There is another question by Rayan that is asking, Ciao Rayan, that is asking, there are instruments measuring AE in the South Pole. The answer is no. The AE is defined, is by definition given by the measurements in the northern hemisphere And this is because in the past we have not measurements from the southern hemisphere. For sure, you can calculate something similar by using the measurements now available at the southern hemisphere, but this is not the case for the, let's say, official AE index.
Yes, these indices, we forgot to say that these indices are released, are provided by World Data Center, so we can say certified. They are released according to some standards to homogenize the information all over the world. And traditionally, for KP and for AE, the measurement comes from the Northern Hemisphere. In principle, we can derive also indices from the Southern Hemisphere, from the magnetometers measurements from the Southern Hemisphere, but they are not certified. They are not given by this World Data Center as the standard indicators, the standard indices. There is another highlighted very important index that we didn't have time to mention, that is the polar cap index, that is more related to the region that is confined by the northern boundary of the auroral oval, as Claudio described some slides ago. And the polar cap index is released for Thule, for the station in Thule in Greenland, for the North Cap, and for Vostok station, from Vostok station measurements for the southern hemisphere. So these are certified. Why we need the long data series, the historical series of these indices? To reconstruct the climate, so the space climate that we mentioned as a possible background. So it's also important to have long data series and historical records of the indices themselves to reconstruct the general assessment of the climate. Other questions, Claudio? No? Okay. Meanwhile, we wait for additional questions, if any. On behalf of Dr. Molina, I have to ask you, who of you would like to take the exam at the end of this course? They have to send an email to Dr. Molina, then she will provide all the information for the exam. So please do it as soon as you can, if possible, by tonight or tomorrow morning at the latest, to give us also this information to prepare the material for the exam. Okay.
Okay, so no other questions, so we can close the first day of this course. For sure, you can think about all the stuff we have shown to you today, and maybe the day after tomorrow we can start with some questions if you have any. So thank you, everybody. Thank you for being here for such a long talk, and see you the day after tomorrow.
Thank you. Bye.